In this video, we're going to continue our discussion of line integrals by working another example. So we have the line integral over path C of 3x squared plus 3y squared ds. And the C is the right half circle of x squared plus y squared equals 9. I drew that to save some time. So if you'd like to stop and draw that, that's our path, that right-hand circle. I also even gave the points that it starts and stops at. It didn't really give me that. I will just make sure any assessment questions are not ambiguous in this case. So I'm going to start at the bottom, go to the top. We have to create, if we remember our definition here, let me go and grab this. I'm going to, actually it still may be, nope, it didn't paste. Let me grab this definition from this last problem. Forgive me. Copy. We're going to use this definition here. There is my definition. I can even get rid of these highlights. There is my definition of my line integral. I need a, this says to, I'm just going to highlight these again, put the integrand in terms of x and y, or a t. We're going to do that. But it also needs a path with a derivative and its magnitude. They did not give me a path defined as r, so we have to do that ourselves. Now, I want to go around that circle, r of t. I know I'm going to let x be cosine and sine be y. So, and then we put our radius just right in front of that. So 3 codius t, what is that? 3 cosine of t, and then 3 sine of t. And then we have to figure out a way for t. We want t to jump. We want to go from one end to the other. So to get cosine down there, we want negative pi over 2. And to get the top one, we also want pi over 2. So we don't want to do 0 to t. You could have probably, of course, you can create any kind of path with this following that. You could have found a way to do t from 0, t from 0 to 1. You could have came up with anything like that. Now, we just want to be careful with our bounds, plugging it in when we get there. Okay, so we have r prime. Okay, it's going to be negative 3 sine t, and then 3 cosine t. All right, cool. We have our path, we have the bounds, and then we'll just do our line integral. We'll plug it in as we go. So that's 3x squared plus 3y squared ds. And we're going to go ahead and make our changes. T equals negative pi over 2 to t equals pi over 2. And then we are going to rewrite. So this is 3 times 9 sine squared, or sorry, we got to do the right ones. X is cosine. So it's 3 times 9 cosine squared plus 3 times 9 sine squared times the, oh, we didn't do magnitude. Let me scoot this down. Let's do magnitude. You can see that this is going to work out. Sine squared, cosine squared. We're going to get a 3 squared, which is 9, but then we'll take the square root. We're going to get a 3. Follow that through if you need to. All right, I'm going to go ahead and rewrite this. All right, and we get, okay, I'm just going to pull actually the whole number out. I'm going to get 3 times 9, which is a 27 times 3. That's just an 81. So I'm going to pull 81 out. And then I just have cosine squared t plus sine squared t. But I pulled out all those numbers already. dt. This is nice and easy for us. We have 81. And I'm going to go ahead. That's a 1. So if I do it, I get a t. And then I'm just going to run it from negative pi over 2 to t equals pi over 2. Be very careful because it's very tempting to say, oh, that's going to be 0. Let's make sure. So I got pi over 2 minus 81 negative pi over 2. Do you see how it makes a positive? So we're going to get 81 pi plus 81 pi over 2. That's going to be 162 pi over 2, which is just back to the 81 pi. So whatever this line integral represents, the answer is 81 pi there. Be very careful with your, I think even looking at my example, I defined my path a different way. So there are multiple ways. I think I defined my path where t was between 0 and pi. All it did was help my final calculation out. I didn't have to plug it in twice, but it doesn't matter. We can define the path an infinite number of ways.